All right, so we're gonna learn how to solve systems of linear equations. What is a system of linear equations? Well, it means an equation with one or set that has one or more equations in it. We're going to look at two equations, okay? And what does it mean to solve a system graphically? It means you're looking for the places where the two graphs do what? Intersect. Yeah, that's the key word right there. We want to know where they intersect. So when we do these graphically, we're going to do them by hand graphically, not on the calculator graphically. So here's the instructions. In order to graph linear equations, and by the way, how do we know these are linear? They're not square. They're x to the what? They're x to the first. That's how we know they're linear. Again, how do we know they're linear? They're x to the first. That's how we know they're linear. So to graph linear equations, we want them to be in slope-intercept form. That's mx plus b. So we group the equations together with an open brace like that. So I'm just going to work straight down. The first one, I'm just going to bring the 2x across and put it in front. It becomes minus 2x minus 3. There it is in slope-intercept form. The next one, I have to do two steps. I'm going to keep the negative 2y by itself, and it becomes negative 3x minus 8. But now I have to do what to solve for y? Divide by 2. So I have to rewrite the first equation, and now I'll divide both sides by negative 2, or multiply both sides by negative 1/2. That's going to give me a positive 3 over 2x, and then 8 divided by 2 is positive 4. So there you go. There are your two equations. Questions on that so far? Again, notice I'm working straight down, and I'm bringing down both equations as I go. So even though that first one was ready to go after one line, I had to rewrite it in the second line because the second guy wasn't ready to go. Now I'm ready to graph both of them. Let's choose flavors here. I'll graph this one in blue, and I'll graph the other one in red berry. Okay, boysenberry. It's kind of a purplish color. We'll do blueberry for the first one. We go down to negative 3, and the slope is negative 2. So down to negative 3, 1, 2, 3, and the slope is negative 2. So down 2, right 1, down 2, right 1, or up 2, left 1, up 2, left 1, up 2, left 1. All right, and then we draw a line through here, and we can snap it, which is pretty nice. Make it perfectly straight. Looks decent. All right, and then in red berry, we'll go up to 4, and then up 3, right 2, up 3, right 2, up 3, right 2. So 1, 2, 3, 4. There's the y-intercept. And up 3, right 2. Or down 3, left 2. Ah, that's an important point. I kind of missed that, but you can move it, right? There we go. So it appears that they intersect at this point right here. That looks like the common point of intersection, which is what? Negative 2, comma 1. Negative 2, comma 1. So whenever you're sketching these functions, it's very important to sketch them as accurately as possible, which is easy to do with lines, especially when you have the coordinate grid given to you. Instead of just like making 3 dots, you might just want to like use the slope to get your dots all the way across, and that way, when they do intersect at a nice grid point, we can find it. Now, had they intersected somewhere like this, let's just say, for instance, they intersected like that. Would you be able to tell exactly where the point of intersection is? No. So you're not going to be given things like that to solve by hand. That's where the calculator would come in handy. We would graph this in y1, graph that in y2, and then second trace number 5. We've done that before, right? Second trace number 5 is intersect, and then enter, enter, enter. Come on in. All right, everyone warm? It was 35 degrees this morning at my house when I left. But it's supposed to get up into the 60s today. So a beautiful day to be indoors. I wish we were outdoors. Oh well. Until we get that waterfall, I made a suggestion that they install a waterfall, and we can use the waterfall curtain itself as a screen onto which we can project, and then we could sit outside under the roar of the waterfall, and we can watch the waterfall, and this will be projecting on the waterfall as it falls, and I could be talking over it, teaching you math. But they haven't put that waterfall in yet, much less install the projector that would have to go in front of the waterfall. So until that happens, I guess we're stuck learning math indoors. Okay? Unless I could take the chalkboard outside. No, we don't want to do that. All right. So we already talked about a system of linear equations. We're going to learn three ways to solve them in this section. The graphical method, which we just went over. Substitution, which is one of my favorites, if not my favorite. And then the elimination, which is also one of my favorites, if not my second favorite. These are all of my top three methods, by the way. There are other methods like guess and check. Guess and check does not work too well. And then there's other methods called like matrix multiplication. There's augmented matrices, and there's even something called Cramer's rule. We're not going to learn all that. These are the top three for sure. All right, so for the graphical method, let's just kind of fill in the blanks down here. Lines that are intersecting will have how many points, how many solutions? Line that intersect will have how many solutions? Yeah, like we had in the warm-up, you're going to have, let's just color code it. We'll have blueberry coming in here. We'll have red berry coming in there. And then we'll write the answer in green. There is one solution. One solution. Okay, what if we graph the two and they have the same slope but different y-intercepts? That means they run parallel to each other. How many solutions will they have? Zero, right? Because the solutions are the intersection points. The solutions are the intersection points. Okay, now two lines that coincide with each other. What does coincide mean? It means that the first one looks like that, and the second one looks like that as well. That means there's infinitely many solutions. Yeah, they literally are laying right on top of each other, hiding each other. So in this case, you're going to have infinitely many solutions. Infinity many. Infinitely many. Okay, so most of the time they intersect one time and we find it like we did in the warm-up. Every once in a while they'll run parallel to each other, no solutions. And we're talking about the Cartesian plane, the flat two-dimensional, flat Euclidean geometry plane. There are times where parallel lines can intersect if you're looking at like a curved geometry, but we're not looking at curved geometry. Okay, solve the system using the graphical method. Hey, little deja vu, isn't it? Yeah. Let's do this one together rapidly, okay? Now that we know the technique. Step one, you're not going to be given the instructions. Step one, put them both into slope-intercept form. Okay, so we're going to get y is greater than negative 2x plus 5. And over here we get negative 3y is greater than or equal to negative x plus 6. Now what is different about this than from the warm-up? These are actually inequalities, which only make it slightly more exciting. Slightly more exciting. All right, the first one is ready to go, so I just recopy it. Y is greater than negative 2x plus 5. The second one, I'll switch to red berry. When I divide by negative 3, since it's an inequality, here's what makes it partially more exciting. I can't forget to remember to do what? Flip the inequality. Now it's less than or equal to, and I get positive 1/3 x minus 2. Okay, let's review how to sketch inequalities compared to equations. First of all, we're going to need the equation of the line negative 2x plus 5, or the graph of the equation. All right, so we're going to go up to 5, and we're going to go down to right 1. Go up to 5. 1, 2, 3, 4, 5. There's the dot, and we go down to right 1. Let's get a couple more. Down to right 1, down to right 1, so on and so forth. You can keep going if you want, all the way to the end of the table if you want. Looks like that. Or you can go up to left 1, up to left 1. Now, because it's not an equation, here's what we do. If it's a strict inequality, less than or greater than, they get graphed with a dotted line. Okay? They get graphed with the dotted line. So this one, I have to connect it us with the dotted line. Now, the cool thing about Notability is you can switch your lines quality. I think you used to be able to. I forgot how to access it since the update. Keep scrolling. Uh-oh, I moved it. I didn't want to move it. I scrolled. I go to the colors, and then keep scrolling. Up.
No, like on the color one, like on the color. Scroll up. Oh, on the color line. Scroll on the color line.
Show me where. Here.
Oh wait.
Oh, it's on the color line. Oh, on the color line. That's what you said. Okay, So I'm going to switch to dotted. And the reason I want to do that instead of drawing it by hand is because I like the snap feature. You can see why. I draw my lines kind of crooked. Yeah. So there's my dotted line. Now I can move it. There it is. Okay. It looks beautiful. Now there's one last thing that we have to do. Switch to your highlighter and switch to kind of a light color, the same color you graphed the line with, but a lighter shade. Okay. Now we're going to shade above or below depending on what it says. Okay. If it's greater than, whoa, now I'm writing with the dotted line. I don't want to do that. Okay, on the color, there it is. So if it's greater than or equal to, we're going to shade above. And if it's less than or equal to, we're going to shade below. Okay, greater than means above, yes, yes. Less than means below. Okay, now let's get the other contrasting one up here. If it's greater than or equal to or less than or equal to, then we graph it with a solid line. So there's two things that we're looking at here. Is it a strict inequality or is it an equal to inequality? If it's a strict inequality, it's dotted. If it's an equal to inequality, it's a solid line. And then we look at, is it greater than or less than? If it's greater than in any form, we shade above. If it's less than in any form, we shade below. So for ours, it was greater than dotted, and then greater than we shaded where? Above. So I'm going to switch back to my shader, and I'm going to shade above. So it's all this right here. We shade above all the y values. So all of these values in the shaded region will make that equation true. Will make that inequality true. Okay, now let's switch to red. It is less than or equal to, so I have to make it a solid line, right? Because it has the equal sign, it's solid. So I go down to 2 and then up 1, right 3. Down to 2 and then up 1, right 3. Up 1, right 3. Oops, I didn't do right 3. Sorry, let me try that again. Let me count better. Up 1, right 3. 1, 2, 3. There it is. Up 1, right 3. There it is. And then we do that with a solid line. Yeah, solid line. Yes, correct. True. There it is. Boom. And then I look over here and I decide where to shade. So let me switch to my red shader. It's so much fun choosing all of these colors. All right. Do I shade above or below if it's less than?
Below.
Below. Okay, so then I come over here and I shade below, everywhere below the line. Now you see there's a place over here where I'm shading twice, where the shading overlaps. That's the solution to the system of inequalities. Okay, so what is the final solution? Let's go to a darker shade here. It's going to be anything that's on this line and in this shaded region right here. Anything that's in this shaded region is going to be an ordered pair that satisfies both sets of inequalities. Okay, so it says to. It's hard to write a solution algebraically that includes all those points. Okay, that's why it just says this: identify a point in the solution set. Identify a point in the solution set. So come over here to where the shading overlapped and pick your favorite point. I'm going to pick this one right here. How does that look? Is that in the shaded region? Yeah. Let me get the coordinate to that. It's 1, 2, 3, 4, 5, 6 over 6 down 2. So 6, -2. Are there more than one correct answer to that? Yeah, so when you're doing your quiz, when you're taking your test, there are going to be multiple solutions. I'm going to actually have to check to see if your point that you chose is in the solution set. How do I get this back over here? Oh, there it is. I did it and I didn't even know how. The solution set is contained in what quadrants? Primarily, what quadrant do we call that down there that we're shading in, where my point is? This is quadrant 1, and then we go left to quadrant 2. This is quadrant 3, and this is quadrant 4, okay? So we know it's going to be in quadrant 4. And we usually do that with Roman numerals. But and 1, yeah, because that red line is going to keep going up. I don't really have the room to draw it here, but I can see that it will continue up into quadrant 1. So it does go into quadrant 1. Will it ever creep into quadrant 2 or 3? No, because it's staying to the right of, if you will, the blue line and below the red line. So it has to stay over there. All right. So now we know how to solve system of equations uh, and graphically, and we know how to solve systems of inequalities graphically, right? Which is different than giraphically. How do you solve equation giraphically? You do it with a long neck, right? Let's see if I can draw a giraffe here.
That's really good.
Yeah, wait till you get to the feet. It's got a little bushy tail. It's
Jumping over something.
Yeah, it's a 3D image. His butt is further back and his front legs are closer to us. So it's not like he's standing sideways. He's kind of facing us, you see? And then he's got a spot here. And I know you've seen the meme, but it's always a curious thing. If he were to wear a necktie, would he wear the necktie up here? Would the necktie be worn right there? Or would the necktie be worn right here? At the bottom? I think gravity would make it fall to the bottom, right? Over time, it would slide to the bottom. You wear it at the bottom of your neck. Okay, so yeah, I think he would look spiffier with it at the bottom as well. And it's easier to keep on. So yeah, this is maybe where he wears his scarf. He wears his scarf at the top, and he wears his necktie at the bottom. Yeah, yeah. A turtleneck. Yeah, I think that would probably go all the way to the top, don't you? Yeah, yeah. Okay, so that's how you would solve the equation giraphically. And now I just messed him up with 2 weird eyes. Okay. Let's go to my favorite method of the 3, the substitution method. Okay, the substitution method is doing it exactly as it would imply. You're basically taking one equation and you're substituting it into the other for something that's equivalent. Right? You're taking one equation and you're substituting it back into the other one for something that's equivalent. So let's see what the instructions say to here. To clear any equations of a fraction, multiply the entire equation by the common denominator. Okay. That's if you're afraid of a fraction. Are y'all afraid of a fraction? No. So I'm gonna skip that step for now. We're not afraid of fractions. This is the most important part that you want to start with. Solve one of the equations for one of the variables. It doesn't matter if you're solving for x. It doesn't matter if you're solving for y. It doesn't matter if you're solving the first equation. It doesn't matter if you're solving the second equation. Whichever is easier. You solve one equation for one variable. So let's take a look at this down here. Would you like to solve the second equation for y?
No.
I wouldn't either. That would be the most challenging one to solve for. Yeah. I would say solve the first equation for either y, since it's already 1y instead of x. X is a 4x. Solve it for y, or solve the second equation for what? X. Either one of those two would be just as easy. I don't really care which one. Let's solve the first equation for y, just because it's listed first. So I'm going to draw an arrow like that. That shows that I'm using the first equation. And all I got to do to solve for y is to bring the 2 across, and I get 4x plus 2. Okay? Now, here's what I would like you to do. Box it, because you're going to have to come back to that. We now have, oops, I got rid of the box. Oh, I know what I did. I put 2 fingers down. You don't want to do that. Y is now the same as 4x plus 2, and 4x plus 2 is now the same thing as y. They mean the exact same thing. Okay? So what am I going to do? I am now going to plug this into the second equation for y. And here's what it looks like. X minus 3 halves times parentheses equals negative 2. And now I'm going to substitute in there, and I get 4x plus 2. It is a negative 2. Why did I put 4x plus 2? I'm still thinking of that giraffe. I'm still thinking of the giraffe. I would not recommend doing these problems giraphically. There's too many things that makes your mind wander. You can't focus. Okay? You want to do them porpoisely or purposefully. Isn't a porpoise the same as a dolphin, kind of? More like a platypus, a porpoise? It is 4x minus 2. I'm glad we caught that. Okay? So I substitute in. All right, now I have one equation with one unknown. Everyone see that? One equation with an x. Now I just got to solve for x. Okay, that's my goal. Solve for x. Now to do that, I'm going to have to distribute like this. Okay? So here we go. Let's distribute. The x goes along for the ride minus. What is 3/2 times 4? That's really the same as 4 divided by 2 times 3 or 3 times 4 divided by 2. You get 6, right? People like to multiply first. 3 times 4 is 12. 12 divided by 2 is 6. But I think I've been trying to get y'all to go small before you go big. Divide first. 4 divided by 2 is 2. And then 2 times 3 is 6. So either way, the numbers are pretty manageable here. You get 6. So we get 6x. And then a negative times a negative is a positive. And what's 3/2 times 2? 3. So that's what happens when we distribute. And that equals negative 2. Now I combine these two to get negative 5x. I'll bring the 3 across and it becomes a negative 3. What's negative 3 minus 2? Minus 5. Can you do that in your head? Can you do those two things in your head? Bring the 3 across and call it negative and combine it with the negative 2 at the same time? This is honors. Try to make yourself do stuff like that. And now we'll divide both sides by negative 5. It divides out on the left, and negative 5 divided by negative 5 is 1. Yeah, 1. So we found the first coordinate. If you want to box it, you can, but we're not done. Guess what we do next? We plug into the first equation. That's why we boxed it. Okay? So now we can say, y must equal 4 times 1 minus 2, which means y equals 4 minus 2, which means y equals 2. So we used that equation twice, didn't we? The one that we solved for initially for the variable, we used it twice. We used it once to plug into the other equation, and then we used it at the end to find the other variable. So you will be using it twice.
Wait, so if you like went to the beginning and you would have looked for x and what x equals, like.
Yeah, you want to do it the other way? We could do it the other way just to verify it works. Now, here's what you want to do. So your solution as an ordered pair is going to be 1, 2. We want to write our solution as an ordered pair. X, y. All right. Riley said she wants to see it the other way, which is fine. So let's have y plus 2 equals 4x, and x minus 3/2 y equals negative 2. If I want, I can solve the bottom equation for x. X is going to equal positive 3/2 y minus 2. Let me box that. All right, now what do I do with that? I plug that into here for x, and I get y plus 2 equals 4 times x. Well, that's 3/2 y minus 2. That's the substitution right there. We're substituting in for x what x is equal to. And we always want to put parentheses when we substitute, because more than likely we're going to be substituting something that has more terms than what it started with. All right, now we just need to solve for y. Solve for y. Well, we distribute again. So we get y plus 2 equals, what's 4 times 3/2? Well, what's 4 divided by 2? 2. What's 2 times 3? 6. So we get 6y minus what? 8. 6y minus 8. Now, I'm going to bring the 6y across. That becomes negative 6y. Negative 6y plus y is negative 5y. And then I'm going to bring the 2 across over here, and it becomes negative 2. What's negative 8 minus 2? Negative 10. So I did two things there. I collected my y's on the left and combined them, and I collected my numbers on the right and I combined them, and then I divide both sides by negative 5, and what's negative 10 divided by negative 5? 2. Is that the same y value that we found over here when we substitute the other way? Yes, we just find them in the different order. So when we did it the first way, we found y equals 2 second. Now we're finding y equals 2 first. And now we do the same thing. We plug it back into here. Whoa! Plug it in there, and we get, so x is going to equal 3/2 times y, which is 2, minus 2. And then we just evaluate, that's 3 minus 2, and we get x equals 1. So we can box that. There's a lot going on here, so boxing it kind of helps you keep track of the important stuff. And so now we'll say the solution is the ordered pair x comma y. So even though you found the y first, you don't list it as 2 comma 1. You always list the x first and the y second. Substitution. Pretty nifty. Now notice we didn't have to use this. It says to clear any fractions, multiply the entire thing by the common denominator. You could have done that in the beginning. Like if you wanted to, you could have multiplied both sides of this equation by 2. And what would that have looked like? If you distribute the 2, you get 2x minus 3y equals negative 4. And then you can solve the first one for y and plug in and do all that stuff. But that's only if you're afraid of fractions. We're not afraid of fractions, and the fractions work themselves out anyway. So I would tell you, since this is an honors class, know that you can do that, but also embrace the fractions. Don't be afraid of them. Halloween is over. Boy, that'd be a scary Halloween movie, right? The name was just called Fractions. People run the other way. They wouldn't even go see it in the theater. They'd be too scared. Fractions. No! Can't we just multiply both sides by the denominator and get rid of them? Well, that's the only thing that kills them. But you got to get close enough to them to do that. People don't even want to do that. Notice it says right here, note, if your answer is not written as an ordered pair, you will lose points. You will lose points, like a sock in a dryer. You will lose points. All right, so we have a couple of ways to do things, right? We can solve systems graphically. We've got to be very meticulous when we sketch them. We can solve them graphically, which kind of takes our mind off the task and gets us sidetracked, where we can make careless mistakes. I wouldn't recommend that. We can solve them using the substitution method. And then the last method is called the elimination method, which is basically it's a take on linear combinations. Okay, so here's what the elimination method is. I'm just going to walk you through it. The elimination method here is we're trying to eliminate one variable by adding the opposites. Now here's kind of the rules of the systems. You can multiply, like I did up here, you can multiply both sides of the equation, either one of the equations or both equations, by any number. Like if I multiply both sides of this equation by 2, it doesn't change the solutions. I could have multiplied the top, both sides, by 100 if I wanted to, and it wouldn't have changed the solution to the system. So with that in mind, what you're trying to do is you're trying to get your x terms written first, your y terms written second, and your constants written third. So if they're not lined up like that, if they're not already written in this x, y, a format, you want to get them in the x, y, a format. So it's ax plus by equals c format. That's what you want. And you want them both to be that way so that they line up. All right, now your goal is to multiply one of them or both of them by a number so that your coefficients are opposites of either the x or your coefficients are the opposites for y. Now, I see that the x has a 1 in front of it right here. So if I wanted, I could multiply the top equation by negative 2/3. That's what it'll look like. I can multiply the top equation by negative 2/3. Let's just think about for a second what that would do. If I were to multiply both sides of the equation by negative 2/3, and that I put it out front instead of putting it like this in parentheses on both sides, but we are going to multiply both sides by it. If I distribute the negative 2/3 here, I would get negative 2/3 x, and then I would get positive 8/3 y, yucky, yucky, gross, gross, but not too bad, equals negative 16/3. You just multiply straight across. If I kept the bottom to itself, then I get 2/3 x minus 3y equals 3. Now, here's the beautiful part of these systems of equations. I can add or subtract one equation with another equation, and I don't change the solutions to the system. So now that they're stacked like this, you would still have this right here. Let's add these vertically. Put a big plus sign in the front. Why is this going to work? What is negative 2/3 x plus 2/3 x? 0. I eliminated the x. Yay me. I eliminated the x. It's gone. And now I just continue adding. What's 8/3 minus 3? Does anyone have a calculator, or do we need a calculator? 8/3 minus 3. 3 is how many thirds? It's 9/3, right? 3 is the same as 9 divided by 3. So what's 8/3 minus 9/3? Negative 1/3. Now, if you had a calculator, you could do it on the calculator. You could just hit 8 divided by 3 minus 3, and then hit math, enter, enter. And it gives you negative 1/3. All right, what is negative 16/3 plus 3? Well, 3 is the same as 9/3, yes? 9 divided by, so what is negative 16 plus 9? You can do it on the calculator. You can do negative 16/3 plus 3, enter, and then hit math, enter, enter, and it'll convert it to negative 7/3. Now all we got to do is solve for y. The x is gone. We just got to solve for y. Let's review. How would we solve for y if we have a fraction there? Multiply both sides by what of the fraction? The reciprocal of the fraction. What's the reciprocal of negative 1 over 3? Negative 3 over 1. Negative 3 over 1. If it's negative, you want to keep multiplying it by negative because then that becomes a positive. So these divide out on the left side. And you're left with y equals. And over here, the 3's divide out. And the negative times negative is positive. And we're just left with 7. There you go. We get y equals 7. Now, there is an x out there that's still left to find. So here's what we do next. Like we did in the substitution, I got to plug this y back into the first equation or the second equation. It doesn't matter which one. Which one looks easier to work with? The first one. So let's plug it into the first one. I'm going to get x. I'm going to put number 1. I'm putting number 1. You can call the top one number 1, the bottom one number 2 if you want. I'm plugging back into number 1. So I get x minus 4 times 7 equals 8. And that means x minus 28 equals 8. And if I bring that across, I get 28 plus 8, which is 36. And now because I don't want to lose points, I'll say the solution is parentheses 36, comma 7. That's where those two lines intersect. The elimination method. Is that the only way to do that? No. Let me show you another way. As long as you're eliminating a variable, you could do it any number of ways. X minus 4y equals 8. 2/3 x minus 3y equals 3. This is where some people multiply everything through by 3 because they're afraid of the fraction. But I'm not afraid of the fraction. So I'm just going to leave it. Here's what you could do. If you're unsure on what to do, let's say I want to eliminate the y. All I got to do is almost do like a crisscross applesauce. Since there's a negative 3 down there, I'm going to multiply the top by a negative 3. Since there's a negative 4 over there, I'm going to multiply the bottom by positive 4. I want them to be opposite signs. So in other words, I just took that number and put it over there, and I put that number over there. But I want the signs to be opposite. So instead of multiplying by the exact same number, since I want the signs to be opposite, I'm going to let one of them be positive. Let me show you why this works. It's just helpful if you see why it works. If I multiply through by 3 all the way through now, I get negative 3x plus 12y equals negative 24. In the bottom, if I multiply through by 4, I get 8/3 x minus 12y equals 12. Okay? And now what do you notice about the coefficients of my y? They're opposites, right? That's why I did one of them as plus, one of them as minus. So you can always do that. Yes, if you wanted to do positive 3, if you wanted to do positive 3 and negative 4, that works too. So you can always kind of multiply by the other constant, just make one of them the other sign. Just change the sign on one of them. If you change the sign on one of them, then you're guaranteed to have opposites, okay? And now if you add here, let's see if we get the same thing. What's 8/3 minus 3? Well, 3 is 9/3. What's 8 minus 9? negative 1. So we get negative 1/3 x. The 12s cancel, and now I get negative 24 plus 12, which is negative 12. And now if I multiply both sides by the reciprocal of negative 1/3, which is negative 3 over 1, those divide out, and I get x equals positive 36. And then how would I find the y value? I wouldn't plug it back into one of these. No, because those are bigger. I would plug it back into one of the original, namely this one here. And I'm not going to do the work, but guess what we're going to get for y? We'd get 7. Yeah.
Wait, so when we plug in the value, can it be for either one of those?
Uh-huh. Yeah, you could plug the x value back into, we have 4 equations. And you can plug the x back into any one of them. You can plug it into this first one, the second one, the third one, or the fourth one. But which of those 4 is the easiest? The first one is probably the easiest. Okay, so you can plug that 36 back into any of them. And you can get y equals 7. So that's the elimination method. You're trying to get the coefficients to be opposites. That's it. And you can multiply through by any number to make it an opposite. It's typically easier if one of your coefficients is already a 1, because then you can just look to see what the other one below it is. Oh, it's a 2/3, so I'm going to make that a negative 2/3. I'll multiply by negative 2/3. Okay, let's answer these questions and we're done. Sometimes when solving a system of equations algebraically, both variables are eliminated. Ay caramba. If you get a result of 2 numbers that are not equal, like what if you're solving and you end up with 1 equals 4? Is that true? No, because 1 is not equal to 4, there are no solutions. And the lines are parallel to each other. Just think, when you get 1 equals 4, tell yourself, no way, no solution, no, 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 no. 1 does not equal 4, no. Solutions? No. It's just no all the way across the board. No, no, no. They're parallel, there's no solutions. But sometimes if you get rid of the variables and you end up with a true statement, like 3 equals 3, now you're like, so true, right? True, you're like, yes, 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 yes. Now how many solutions are there? Infinitely many solutions. Because the 2 lines are coinciding with each other. It really means they're the same line. If 2 lines coincide with each other, that's another way of saying they're the same line. So does 3 equals 3? 3 is the same as 3, right? So the same line, there's infinitely many solutions. Okay? I like the no one better, right? No, not on my watch. Get that stuff out of here. No. Don't make me sick my pet giraffe on you. He's dressed to kill. He's got 2 neckties on and a scarf. Don't make fun of his eyes. It makes him angry. Okay. Any questions? The homework is not due tomorrow. So here's what's happening. The homework is due Monday at 9 a.m. So you have all of Friday in class to work on it. Does that make sense? Is that good? So I'll be around tomorrow if you have any questions while you're working on it. You're like, I don't like fractions, sir. How do I get rid of them? And I'll tell you, you should really learn to embrace your fractions.
For number 1, do I have to get a graph, draw a graph?
Graphically, the system is shown below represent 2 lines. Oh, no, because it's asking you a theoretical question. Graphically, if you were to do it, the 2 lines which are those, yeah, you have to just do a real quick sketch. Are they going to be 2 separate lines? Are they the same line, or are they parallel to each other? We're not trying to find the actual solution there. All right. On your mark, get set, go.